Welcome to Robo's Adventures. Today Robo will be learning about one variable measurements. Today Robo and his classmates are traveling to a cross-country running practice to measure some data. For their first task, they are asked by their teacher to measure the distance they travel while they are on the physics truck, which is converted to a bus. During the trip, they're also asked to look at the speedometer of the vehicle at a specific point in time to measure its speed. They're also asked to discuss how confident they are in the number that they have chosen. Robo chooses to record the speed of the vehicle at approximately 0.1 hour or 6 minutes. Robo looks at the dials on the speedometer carefully and uses the tick marks concluding 10 kilometers per hour intervals. It then draws the location of the dials in a straight line. Robo knows that the dial is between 60 and 70 kilometers per hour, and thus it can say with certainty that the speed is somewhere between those two numbers. Robo also knows that the number is closer to the 60 compared to the 70. In its mind, it draws a halfway point to estimate where the point is. Using this line, Robo becomes more certain that the number is somewhere between 60 to 65 kilometers per hour. It will estimate that the number is about 63. Robo tells its teacher the observation, the fact that it thinks that the speed is 63 kilometers per hour, but because of the spacing between the dials, it is only certain to about 10 kilometers per hour. Robo's teacher confirms the good observation and tells Robo to write the observation as 63 plus or minus 5 kilometers per hour. This would mean that the speed could be anywhere between 68 to 78 kilometers per hour. Mr. S., Robo's teacher, says that the smallest scale division of an analog device, such as a ruler, is often called the precision of the instrument. For a specific measurement, we can only be certain in this range. Because we use the plus or minus to specify uncertainty, we use half of this increment. Robo analyzes this against the current example. The smallest scale division for the speedometer is 10 kilometers per hour, and therefore the uncertainty is 10 divided by 2 or 5 kilometers per hour. Robo then uses its sensors to further divide the scale into 10 new divisions using image processing. Now Robo can see that the number is somewhere between 62 to 63 kilometers per hour. It could estimate the number as 62.9 kilometers per hour. Based on the new concept that it just learned, the uncertainty would be half of the smallest division. This smallest division here would be 1 kilometer per hour, and half of that would be 0.5 kilometers per hour. Robo asks Mr. S if based on this logic the speed would be 62.9 plus or minus 0.5 kilometers per hour. Mr. S approves this logic with a happy smile. Mr. S also lets Robo know that when writing uncertainties, the uncertainty should have the same accuracy as the number. This is to say that the least significant or uncertain value of 63, which is 3, and the uncertainty of 5 are both multiples of scale 1, whereas the least significant value of 62.9, which is 0.9, and the uncertainty of 0.5 are both multiples of 0.1. This scaling must be used when expressing numbers with their uncertainties. It is incorrect to have different scaling between the number and its uncertainty. For example, 63 plus or minus 0.5 is incorrect, and instead we should use 63.0 plus or minus 0.5. For the next task, Robo wanted to figure out the distance that was traveled. The odometer had shown a value of 123,034.2 kilometers at the start and 123,051.5 when they arrived at the destination. Robo was wondering about the uncertainties of these values as they were no longer using an analog measuring tool. Robo thought that 123,034.2 comes either from 123,034.24 rounded down or 123,034.15 rounded up, and therefore the uncertainty should be approximately 0.05. Robo asked Mr. S if this makes sense, and Mr. S supported the excellent logic to how Robo thought about this situation. Mr. S said that digital scales are slightly different than analog scales as they work in a binary system, meaning they only increase in multiples of 1. In this case of 123,034.2, the least uncertain value is 0.2, which is a multiple of 0.1. The measuring device here can at best do multiples of 0.1. Therefore, 123,034.11 and 123,034.29 might both be read as 123,034.2. Because of this, unless otherwise stated, for digital devices, the uncertainty is the smallest increments. For example, uncertainty of measurement of 350.33 is 0.01, 350.3 is 0.1, 350 is 10, and 400 is 100. Robo recorded this information in his hard drive. It then tried figuring out the distance traveled. Robo knew that the measurement at time 0 was 123,034.2 plus or minus 0.1 kilometer. This would mean that the value could have been at max 123,034.3 and minimum of 123,034.1. It also knew that at the destination, the measured value was 123,051.5 plus or minus 0.1 kilometers, giving it a max and min values of 123,051.6 and 123,051.4 kilometers respectively. To obtain the maximum possible distance, Robo subtracted the largest value from the smallest value. To obtain the minimum possible distance, Robo subtracted the lowest possible value at the destination by the max possible value at the start. Robo calculates the minimum distance to be 17.1 kilometers and the maximum to be 17.5 kilometers. Robo then rewrote this as the average, which is 17.3 plus or minus half of the difference, which was 0.2. Robo showed this result to Mr. S. Mr. S was very happy to see this logic. He mentioned that they will discuss propagation of errors in future lesson, but Mr. S was so impressed that he asked Robo to explain this logic to other students in the classroom. When the students got to the cross-country practice, they were divided into groups of 3. Today, Robo is working with Baba and Negda. They are to measure how far a specific runner has traveled from the starting position after a specific amount of time. Baba is measuring the position of the runner relative to the starting position at 4 minutes, Negda at 6 minutes, and Robo at 8 minutes. Since Robo is a newly built robot, its moving abilities are currently limited and the group is happy to accommodate its needs. Therefore, the group sits together in a location where they can observe the run without having to run around themselves. The field where the runners are running is divided into 100-meter sections with large marks and 20-meter subsections using small marks. Anna is the runner who this group is observing. Anna starts running and at 8 minutes, Robo estimates her position by its sensors and draws an image of it to allow it to report the measurements. From this image, Robo determines that the large divisions is 100 meters, and since it's divided into 5 smaller divisions, the small divisions are 100 divided by 5 or 20 meters. Robo knows that this is an analog device, and thus the uncertainty is half of the precision of the tool. Therefore, the uncertainty is 20 divided by 2 or 10 meters. Robo estimates the number to be approximately 1,390 meters, and therefore the measurement to be 1,390 plus or minus 10 meters. Robo checks for the format and sees that 1,390's least significant value is the 9, and since 90 and 10 are both multiples of 10, the format is correct. Robo shares this observation with the group. Nigda and Baba also share their numbers, but as a group, they're confused. Is this number really a good representation of Anna's run? The group discusses that if Anna was to run again, would the number be the same? What if the runner was not running at 100%? What if they were sick or just warming up? What if they were running with or against the wind or the rain? Mr. S came to check up on them, and the group asked him these questions. Mr. S said that these are all examples of random errors in a measurement. Random errors are often caused due to the inability of the experimenter to take measurements in the exact same way. External factors that would change the measurement in different ways could cause this. Robo asked, how do we reduce it? Nigda suggested, could we repeat the experiment again? Baba confirmed that it makes sense that more data would be better. Mr. S said, these are great ideas. Let's repeat the experiment 3 more times. The more trials, the better. However, we are limited in the numbers of trials in an experiment because in this particular case, we don't want to injure our runners. In most cases, we want to include at least 3 trials for our measurements. Mr. S also asked students to write any qualitative information about the experiment, so if the numbers are vastly different, the students can figure out what might have caused it. Qualitative observations are those that can be observed by our senses, such as visual, smell, or touch. For example, wind and its direction, color, and shapes could be qualitative observations. Quantitative observations are data collection focused on numbers. Examples include time and distance. The group agreed and started the task as Anna ran 3 more laps. The group wrote their observation for all trials. In all trials, the sky was sunny, the runner stretched, there were good visibility, and the rest times were consistent. In trial 1, the wind was moving towards the direction of the runner, and in trial 4, the runner seemed much more tired. Robo then used its camera to capture pictures at a time of 8 minutes for the next 3 trials. Robo also used its skills that it had just learned to come up with 4 measurements for the different trials. Robo spoke to the group and everyone agreed that Anna was too tired in the last run and her performance was not representative of her ability to run. After letting their teachers know, Mr. S said, based on the evidence of your qualitative observation, you can consider the 4th trial as an outlier. An outlier is a data point that differs significantly from other observations. It can be removed as long as there are enough data to support it as an outlier. It's important to use qualitative data to justify an outlier whenever it's possible. More data makes finding an outlier much easier. Now, after removing the outlier, think about how you can represent the 3 measurements graphically and numerically. Some of the ideas that were discussed as a group included max-min lines, whisker plots, points, center, and standard deviation for graphical methods, and average, mean, mode, plus max, minus min, and plus or minus difference divided by 2, and standard deviation for numerical methods. Mr. S suggested that each method has its own advantages and disadvantages. Since in high school level, students often don't conduct too many trials, the recommended method is to use the average for the center of the data and half of the difference between the max and min values for the uncertainty. Standard deviation would be a better method. However, some students have not covered this method at this stage of their learning. Note that you might also see uncertainty calculated by max minus min divided by the square root of the number of trials. Robo now identified the max and min numbers to be from the first and second trials respectively. Robo used the average formula to find the mean. Robo then used the max minus min divided by 2 formula to find the uncertainty of the value to get 1353.3 repeated plus or minus 30. Mr. S told Robo that your reported value should be no more certain than your original measurements. Robo processed this in his CPU. The original measurement had uncertainty of 10 meters. That means that all measurements were rounded to the nearest tens, and the final reported value cannot be more certain than this. Therefore, Robo needed to round both the mean and the uncertainty to the nearest tens. The uncertainty is 30, which doesn't need any rounding. The value for the average is 1353.3 repeated, and that needs to be rounded to the nearest tens, and therefore it becomes 1350. The final value can be reported as 1350 plus or minus 30. Robo then tries to visualize this and compare it to the original points. Robo draws the center of the data using a solid circle and then adds 2 solid lines 30 meters away from the center because of the uncertainty. Robo then connects these 2 lines to the center. Robo can see that trial 2 and 3 are well captured, while trial 1 is not within the region, although it is very close. Baba and Negda have similar results, and they comment on the fact that mathematical models will always have their limitations. This ended today's journey of Robo in learning physics. The students were heading back to the school, and Mr. S asked them to think about the limitations of their measurements and what are some ways in which they can improve them. Could they use their group's data to find the speed of their runner? Robo has processed so much data today and is looking forward for a nice rest before it starts reviewing the content. Robo is looking forward to the next journey in the physics class.